Good evening, students. Am I audible?
Yes, sir.
So I think we are done with the 5th chapter, right?
Yes, sir. Yes.
Next chapter that we are going to start is the 6th one, which is called as the electromagnetic induction. I hope you're able to see my screen, right? So write down the heading. It's chapter 6, which is called as the electromagnetic induction. In simple, we can also call it as EMI. Okay. If I have to give you an introduction of this chapter in one word or in a single statement, it is exactly the reverse of what you have studied in the 4th chapter. Okay. So what was chapter 4, guys? It was
Moving charges in magnetism.
so moving charges in magnetism. That's right. So what did we deal in this chapter? How moving charges can produce
Magnetic fields.
magnetic fields, right? So this chapter is about how to use magnetism to make the charges move. That is, 4th chapter was about current carrying conductors have magnetic field around it, and we calculated different magnetic fields depending on the orientation and nature of these materials that were available. Now what we will do, we will exactly do the reverse of it. Okay, so shall we get started? So before I start with the main context of this chapter, see, every chapter has certain important terms that you need to know. So in this chapter, the first and the foremost important term that you need to know is magnetic flux. So here, what does magnetic flux mean? You guys already know what an electric flux means. So what is electric flux?
Number of electric field lines passing through an area perpendicular to it.
Then what do you think magnetic flux is going to be? The
So
number
the
of
Magnetic field
fields,
passing through
right.
some area perpendicular to it.
Please write it down. So number of magnetic field lines passing through a given area normal to it. So number of magnetic field lines passing through a given area normal to it is what we call it as magnetic flux. Okay. So the symbol used for magnetic flux is also phi, but we will use a small suffix here, which we call it as phi b. So how do we write phi b as? If you recollect, phi e is equal to e vector dot a vector, or I can call it as e into a into cos theta. Right? That's a simple thing. In a similar way, what do you think magnetic flux will be equal to? It will be b vector dot a vector, or it is going to be b into a into cos theta, where theta is angle between whom? Angle between the magnetic field and the areal vector of the coil. Right. So based on different types of orientation, the flux can be classified into different types. If theta is 0, you will get maximum flux. Theta is 180, you will get maximum flux in opposite direction. All those things we have already discussed in the electric field concept itself, under the electric flux itself, right? We have done some problems also. Now we will concentrate on something important. So what did we say? What did I say? I told our job is to induce means generate electricity, that is generate current using magnetism. That is our job. So our job is to induce current using magnetism, right? So for that, how is the concept of flux going to help us? That is what we need to think of, right? So how do we solve it? For that, let me show you a small simulation. Just give me a minute. See, see this. So what I have here is a coil. You're able to see a coil, right? And those blue color dots are there on that. That is, those are electrons, right? And what is there on the left of it? We have a permanent magnet, right? Now, when will this bulb glow? Logically, let's think. No? When will this bulb glow?
So when we bring the bar magnet inside those coils,
Why?
so then there will be a flow of electrons. So the magnet electricity will be induced.
Yes, that's right. So so logically, the bulb is going to glow only when these electrons are put into motion. So what we are trying to do is, by bringing this magnet closer, we're able to see that the bulb is glowing.
Motion.
So when I do this, look at the magnetic field lines around the magnet. Look at the magnetic field lines around the magnet and look at the magnetic field lines within the coil also. So what is happening to it? You're able to observe
Electron is moving.
yes, there is an electron motion. So let me do it a little faster. But one thing did you observe? This kind of a glow is taking place only till the time I am able to put this magnet in motion with respect to the coil. Right, now there is a reverse test. We also need to do a reverse test. I have the coil. I will keep the magnet fixed. Now I'll try to move the coil. Is the same thing going to happen? Yes or no? What do you think?
I think yes.
Okay. Let's see. What's happening?
Bulb is
Yes.
glowing.
So both are happening, right? So initial case,
Yes,
what I did, I kept the coil fixed and I moved the magnet. Now I kept the magnet fixed and moved the coil. Now let me try both. It's not working actually. It's not accepting both the fingers. But in reality, what will happen is it will work. Right? So you're able to understand what is happening. So by me moving a magnet or the coil with respect to the magnet, we are able to generate a magnetic field. Now there I get another question in my mind. So I'm moving this magnet, right? Instead of having a coil, had I had only a linear conductor, do you think this kind of a process would have taken place? Did you understand what I asked? You have a coil.
Yes, sir.
Instead
I
of
think the
coil,
current will flow. Sir. That will.
so you say current
So
will.
the current will flow.
So tell me if this is what your understanding is. I want to understand whether this is what you're thinking. North pole, south pole, a linear conductor, and if I'm moving this, You're trying to say that the electrons inside will move. Correct? Huh? Means current will get generated in it. Is that what you're trying to say? Yes or no?
Yes,
I want
sir.
to know.
Yes, sir.
But that is wrong. Yes. But that is wrong. You know,
Why, sir?
this kind of a phenomenon can be observed only when you have a closed surface. Okay. And that was the main reason why I was speaking about flux. So when you talk about a flux, you cannot speak about flux within, you cannot talk about flux passing through a linear conductor because it is not a closed surface. What did you define flux as? It is the amount of field lines passing through a given area. When can area be formed? Only when it is two-dimensional. Means it should be a coil or something. It should be a closed surface to be more specific. Right? So when you talk about the closed surface, area will come into picture and flux will come into picture. And from there only the phenomenon of this kind of induction comes into picture. Okay. And this was first observed by a scientist named Michael Faraday. And this is what he told. When there is a relative motion taking place between a coil and a magnet, the coil is called as a pickup coil because it is the one which is picking up something. Right? It is the coil which is connected to the bulb is called as pickup coil. Okay, pickup coil. So when the pickup coil and the magnet are moved relative to each other, then electricity is induced in the pickup coil. So what is the principle involved behind it? So you're talking about relative motion, right? That relative motion is actually causing a change in flux. Means Faraday stated something like this. The Faraday's law of electromagnetic induction says Faraday's law of electromagnetic induction says that if there is a change in flux taking place with respect to the pickup coil, what will happen? He didn't say current. He told EMF is induced in the coil. So as soon as the EMF is induced, what will happen? Current will start getting generated because the electrons will be in motion. Right? The electrons will be in motion. So this is the statement that he told. And the mathematical expression that he gave is EMF is directly proportional to the rate of change of flux. Okay. So if it is one coil, then E is directly proportional to d phi by dt. If it is n coils, then E is directly proportional to n into d phi by dt. Then EMF will be equal to negative of d phi divided by dt, or EMF will be equal to minus n into d phi divided by dt. And this is happening due to the instantaneous change in flux. Instantaneous change of flux. But there is a possibility where there can be an average change also. When you say instantaneous, when you write it as a derivative of something, right? When we will talk about average, E will be equal to minus delta phi by delta t, or EMF is equal to minus n into delta phi by delta t. So you will use this formula under the average case. But what do you mean by average? When there is sufficient amount of time existing while you do the experiment. For example, 0 to 2 seconds, 0 to 3 seconds. Those are all measurable value. Whereas if this is happening exactly at 2 seconds, means between 1 point some 20 times 9 like this and 2, this is what is called as instantaneous value. Okay. So this is the mathematical expression for Faraday's law of electromagnetic induction, and the negative sign here is the significance of another law called as Lenz law. So Lenz is also the name of a scientist. So it is a significance of Lenz law. What is Lenz law? We will discuss next.
Sir, can you show the Faraday's law of EMI definition? Yes, sir.
No, this is a statement which I randomly wrote. This is a statement which I randomly wrote.
Okay,
You can
sir.
have a look in the notes.
Okay.
You can have a look in the material. Let's discuss the concept alone. So what is the significance of Lenz law? That's what we need to see. Next thing that we need to concentrate is Lenz law. So I will go back to the experiment again. If you observe one thing, now see, one thing you guys observed till now was what? When the magnet was moved, you saw that the electrons were flowing.
They were in motion, sir.
Yes. Now I want you to concentrate on the directions. Now, the north pole is closer to the pickup coil, right? So when the north pole is moved towards the magnet, what is the direction in which electrons are moving?
Anti-clockwise.
Anti-clockwise from which side?
Sir, from left to right.
Actually, when you see from the other side of the magnet, that is when you see from the darker side, it is anti-clockwise. Correct? I'm moving it again. Observe. Anti-clockwise. If I move the same
Yes,
north
sir.
pole away, see what is going to happen.
Clockwise.
It went clockwise. Huh?
Yes, sir.
So again, let's do it a little faster. Anti-clockwise. If I move it away, it went
Clockwise.
right.
Yes,
Right.
sir.
Now, let's try to look at the same thing in a diagrammatic format. If I take this as the coil, okay, my eyes are here. I'm seeing from this side, and the magnet is this side. North pole, south pole. Okay. When I took the north pole close, the electrons, when I see from this side, were in the anti-clockwise direction. Accepted? That you people already saw.
Yes.
The electrons were in
Yes, sir.
anti-clockwise direction. Now, what can I say about the current?
Current was positive in clockwise direction.
Clockwise.
Current is clockwise. So, we will revisit the clock rule. So, if I take clock rule, if the current in the conductor, if you're seeing the current in the conductor in such a way it is flowing in the clockwise direction, then is it not going to generate a south pole?
South pole.
South pole.
Right? So this side means the side which you're seeing is south pole, and this side it is going to be like north pole. What I'm trying to say is this current carrying loop will act like a magnetic dipole. You know this fact, right? When it is acting like a magnetic dipole, then this side was north pole and this side was south pole, right? Now, when you move the same magnet in such a way that the north pole was moved away, then electrons were moving in clockwise.
Clockwise direction.
Current was anti-clockwise.
Means
Anti-clockwise.
this became south pole, this became south pole. Behave. Right. So let's try to observe an important point from north pole. Okay. So when you are trying to bring the north pole, the coil, the side of the coil which is facing the magnet, generated the current in such a way that it had north pole when the magnet's north pole was coming towards it. Means the direction of current, the pickup coil itself chose a direction of current in such a way that left side is north pole. Whereas when you try to move the north pole away from it, the current in the same pickup coil got generated in such a way that there was a south pole generated on the side of the magnet. Right? This is the fact that we have seen. Now let's look at the same thing in a different perspective. When the north pole was moved towards a magnet, did you try to increase the flux or decrease the flux?
Sir, can you repeat it?
I'm asking a question. When you try to take the north pole towards the coil, like in the first scenario, when you try to take the north pole towards the coil, did you increase the flux or decrease the flux?
Increase the flux.
Yes, you increase. Because when the magnet is moving close to something, when you're moving closer to the magnet, you can feel more amount of magnetism. Right? It means increase in flux took place. Whereas when the magnet was moved away from the coil, you are trying to decrease the flux. So can I say here we increased the flux. Here we decreased the flux. Accepted till this point. Any doubt?
No doubt.
So from here only there is an important conclusion that will come. So what I'm trying to say is, okay, when you try to increase the flux, the current in the coil generated in such a way that the loop itself behaved like a north pole. So when this north pole is getting induced, will it try to repel this magnet or attract this magnet?
Repel.
Right. Similarly, when you took the magnet away, it started generating south pole so that it was trying to attract the magnet. Correct? These two are happening, right? So whatever you are trying to do, that is when you are trying to increase the flux, the current got induced in such a way that it was trying to decrease the effect. The current got generated in such a direction that it was trying to decrease the effect. What is the effect here? Because it is because you brought the north pole closer to the coil only, the electron started moving in it. So the electron started moving in such a way that the north pole is generated on the left hand side and it was trying to push. It was trying to push. Means it was trying to nullify the flux. Whereas when you were trying to decrease the flux, it was saying it was trying to pull the magnet towards itself by generating the south pole. Means it exactly tried to do the reverse operation of whatever you tried. When you tried to increase the flux, it tried to decrease. When you try to decrease the flux, it tried to increase. You're able to understand? And this effect is what is observed by Lenz. Okay, this is where the statement comes. Please write it down. The statement for Lenz law. The direction of current induced in the coil, will be in such a way, that it tries to decrease the cause which is producing it.
So decrease the last line.
The cause, CAUSC.
After that,
Cause which is trying to produce it.
okay.
Okay. So based on this Lenz law only, you will be asked to solve many problems, and your job will be to find which polarity is positive, which is negative, and all those things. Okay, this is where people get confused. I'll give you a simple logic. Okay. So if this is the coil, okay, if this is the coil, and you have a magnet like this, whichever pole you're trying to take closer, the current will get generated. If you take the pole closer, then the same pole will get generated on the side of the magnet. Means if you take the north pole close to it, then the north pole should get generated. North pole means current should flow in which direction?
Sir, anti-clockwise.
So from this side, if you see, anti-clockwise current will get generated. Whereas,
Sir, is it in the side of the bar magnet or on the opposite side, sir? You should observe from the opposite side also.
No. I'm saying if you observe from here, if you observe from the side of the bar magnet,
Oh, okay.
then the current will be in anti-clockwise direction. If you obviously when you observe from the other side, current will be in clockwise. That is what I would have written here. See.
Yes, sir.
Okay.
Okay.
Whereas when you try to take the magnet away from it and you observe from the side of the magnet itself, then clockwise current will get generated. Means opposite polarity will get generated. Okay, trust me, there are problems asked based on this concept itself. This is where many people struggle to understand. Okay. Shall we do some problems to understand this concept? This. Give me a minute. Yeah. Listen to this. Now see. Let's start with 6.2. So 6.2, let's try to 6.2 is what we'll start with. So there is a square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. Okay. A uniform magnetic field of 0.1 Tesla is set up across the plane in the northeast direction. The magnetic field is decreased to 0 in 0.7 seconds at a steady state. At a steady rate, sorry. Determine the magnitude of induced EMF and current during this time interval. So how to do this problem? So listen guys, we know that flux is equal to BA cos theta, right? So according to Faraday's law, what did we understand? What should change with respect to time?
So the magnetic, the magnitude of the magnetic field.
Yes, magnitude of the magnetic flux should change. See,
Yes.
flux is dependent. Yes, flux is dependent on three parameters. What are they? Magnetic field, area, and orientation. So,
Okay.
if the flux has to change, what you can do is you can either change the magnetic field keeping the area and theta constant, or you can vary area by keeping magnetic field and theta constant, or you can change value of theta by keeping B and A constant. Are you able to understand?
Yes,
So
sir.
in this question, the magnetic field is decreased to 0 in 0.7 seconds. So initially, what was the magnetic field? It had a 0.1 Tesla. Okay. and it is set in the northeast direction. Northeast direction means how much is the value of theta, guys? Is it not 45 degrees? So initial flux is equal to how much? BA cos 45. Correct, Ada? What is the final flux? It is 0. Why 0?
Sir, 90 degrees.
It is not 90 degrees because orientation has not changed. Magnetic field itself becomes 0. They told no, magnetic field is decreased to 0. So here B is 0. A and cos 45 is the same. So what is going to be the induced EMF? It will be, here you find the magnitude, that is enough. But they are asking magnitude because there is a minus sign in the formula. E is equal to delta phi divided by delta theta. What is delta phi? Phi final minus phi initial divided by delta t. What is final value? 0 minus B is how much? 0.1. Area is how much? Side of 10 centimeter means area is 100 into 10 power minus 4 meter square. The whole divided by 0.7. Okay, if you take the magnitude of it, that will give you the required answer. Okay, Ada? So cos 45 I forgot. Cos 45 is 1 by root.
Cos 45.
Yeah. See, remember 1 by root 2 is nothing but 0.7. 1 by root 2 is 0.7. So 0.7, 0.7 will get cancelled. So you will get 0.1 into 10 power minus 2 or 0.001 volt. You will be able to generate 1 millivolt. Okay. So this is the EMF. How will you calculate the current? I is equal to E divided by R. 0.001 divided by 5. That you find it out, that will give you the answer. So that is going to be 2 milliampere. Okay. 6.3. I want you guys to try it. So there is a circular coil of radius 10 centimeter, which has 500 turns and resistance of 2 ohm, is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. It is rotated about a vertical diameter through 180 degrees in 0.25 seconds. Estimate the magnitude of the EMF and the current induced in the coil. Horizontal component of the Earth's magnetic field at a place is 3 into 10 power minus 5.
Sir, I'm getting 3.8 into 10 to the power minus 3 volts.
3.8 into 10 power. That's correct. So 3.8 into 10.
Okay.
So did you guys understand? Is there anyone who didn't understand how to do this problem or approach this problem?
So should we find the current also?
Oh, that's what they asked, no?
Sir, can you show? Okay, sir.
Current induced.
Okay, so 1 minute.
Or guys, anyone who didn't understand or who wants me to do the problem? Is everyone clear? Give me a confirmation.
Yes, sir.
Yes, sir.
Yes, sir.
That's good. Okay. So this is the Lenz law I was trying to say. When you move the north pole closer, the north pole will get generated in the current carrying loop. When you move the north pole away, south pole will get generated. Okay. So these are all interesting problems. Let's try them out. So example 6.4. Figure 6.7 shows planar loops of different shapes moving out of or into a region of magnetic field which is directed normal to the plane of the loop away from the reader. Determine the direction of induced current in each loop using Lenz law. How to do this?
Sir, we have to use Lenz law.
Yeah, Lenz law is possible. They pulled using Lenz law.
So,
Yeah, you have to use that, but how are you going to use and find it? We need to find the direction of the induced current in each loop. Okay. So for that, I'm just going to give you some techniques, okay, which I follow to solve a problem. See, here if you observe, like how I explained in the case of Lenz law, there I had what? I had a magnet. So you are clear about which one was North Pole, which one was South Pole. Correct, Ada? Suppose you take this magnetic field now. The magnetic field is into the plane. What do we mean by into the plane? Okay. So this is what you need to do. This is activity. See, when you're writing, what will you do? You're facing your notes, right? So you're facing your notes. So let's take your eyes as one of the pole and your paper on which you're writing as another pole. So what pole is your eye supposed to be so that the paper will receive the magnetic field? So which pole has the tendency to receive the magnetic field?
South pole.
South pole means your paper, the paper on which you're writing in this scenario is going to act like South pole. Means you are like what pole?
North Pole.
Your North pole.
North.
Correct? Huh? So this is the first step. I hope this is clear. So you are North pole and paper is South pole. Second, what did I say with respect to Lenz law? you need to see whether the flux is increasing or decreasing. Increasing means same polarity, decreasing means opposite polarity. Okay. So in the case A, when the coil is moving into this magnetic field, when the coil is moving into the magnetic field, can I say flux is equal to BA cos theta? Okay, look at the way I solve it. No? Here, what is constant? They told it is moving into a region of magnetic field which is directed normal to the plane of the loop. So, magnetic field is into the plane. What will be the direction of aerial vector for this rectangular coil? What is the direction of aerial vector? I told you in the first chapter itself. Aerial vector is always taken
Radially outward.
Radially outward in the perpendicular direction.
Yes.
Right here, it is a two-dimensional shape. So what we can do is, for convenience sake, what I will do, I'll take the aerial vector in the direction of magnetic field itself. So here, one point that you might get confused is normal. When we see normal, we tend to write theta is equal to 90 and make this flux as 0. No. When we say the coil is normal to the magnetic field, means the aerial vector of the coil is in the direction of magnetic field. That is a tricky word, okay? I've seen many people doing this mistake. They see the word normal, immediately they put theta is equal to 90, 2 marks gone. Lack of understanding of concepts. So be very clear. Coil is normal to the plane. Aerial vector is in the direction of magnetic field. That is the meaning. Okay. Now, here, what are all the parameters that are constant in the case of flux? I told you flux depends on 3 parameters. What are they? Magnetic field, area, and theta. So which parameter is constant?
Magnitude.
B is constant and theta is also constant.
Yes, sir.
But the flux in this case is changing because the object is given a velocity so that the area associated with the magnetic field is constantly changing. So, when the coil is entering into the magnetic field, is the area increasing or decreasing?
Increases.
Obvious, right? Because more amount of surface will get linked.
Yes.
So area increases. So when area increases, what is happening to the flux?
Flux will also increase.
Yes. So just now I told you one thing. According to Lenz's law, if the flux is increasing, I repeat, if the flux is increasing, what pole will get generated?
Sir, North Pole.
Yes. Means since this coil is facing us, right? We are acting like what pole according to this problem?
South Pole.
There. You are North Pole, I have written it also.
Oh, yeah,
we are North Pole. Right? We are North Pole. So when you are North Pole, the side ABCD which is facing you will also generate North Pole because flux is increasing. Okay, when flux is increasing, it is going to generate North Pole.
North Pole.
So this North Pole, current will be in which direction?
The clockwise.
Direct.
The current will be clockwise.
I have already drawn the arrow marker.
Oh.
Anti-clock. So the direction of induced current is A, B, C, D, A. Okay. Now I want to check your clarity. Do the second problem and let me see how many of you understand. See, one thing then change. What is it? You're still North Pole, the paper is still South Pole. But what is the only thing you need to check? Whether the flux is increasing or decreasing. In the second case, what is happening to the flux?
So it will decrease because the body is moving out of the magnetic field.
Yes. So when it is going to decrease, what will happen?
Sir, it will assume south pole, sir.
It will generate south pole. It will generate exactly the opposite pole of what you are.
Yes, sir.
Your north pole. So it will
Yes, sir.
generate south pole. So south pole means what is the direction of current?
Clockwise.
So AC BA is the answer. Okay.
Yes.
Similarly, do the third problem and tell me.
Sir, in the third one also the flux will be decreasing, sir, because the body is moving out.
Because the object is moving outside, yes, it is going to decrease. So what is going to be the direction of current?
South pole,
Clockwise.
sir. Yes, sir.
So it will
Clockwise.
generate south pole. So it will act clockwise. So answer will be D, A, or A, B, C, D.
Yes, sir. ABCDA.
B, D, A. That's it.
Okay, sir.
So now you understood. So this is how you solve problems. Okay. Let's do another problem based on Lenz's law. So there is a closed loop. Okay, read the question carefully. There is a closed loop which is held stationary in the magnetic field between the north and the south pole of two magnets which are held fixed. Can we hope to generate current in the loop by using very strong magnets? Means what they're trying to say is there is a closed loop. The closed loop is held between a north pole and a south pole. No diagram. Okay. Held between the north and the south pole of two permanent magnets. They're asking, can we expect that there is a current that is going to get generated in this? Can we expect current to get generated in this? Is it possible?
No, sir.
Can we hope? Why?
Sir, both of them are opposite in polarity, sir. So you cancel out.
No, that's not the reason.
Oh.
I told you in the beginning of the chapter. When I did the simulation, I showed you something. I was using one word repeatedly. There should be what?
Motion.
There should be a
Motion.
relative. Here, the word stationary itself tells you that it is not possible. Only when the magnets are in motion, you can change the flux. So the whole objective of this chapter, only one thing. What is it? You have to change the flux with respect to time. If there is no change of flux with respect to time, you can forget about generating magnetic field. Okay. So the answer is no, how much ever strong magnet you are going to use. Okay. No. However strong the magnet may be, current can be induced only by changing the magnetic flux through the loop. Or in other words, if you want, you can write like only if there is a relative motion existing between the coil and the loop. That is also accepted. Right. Second. So there is a closed loop which moves normal to the constant electric field between the plates of a large capacitor. There is a closed loop which moves normal to the constant electric field between the plates of a capacitor of a large capacitor. Is current induced in the loop when it is wholly inside the region between the capacitor plates. Second, when it is partially outside the plates of the capacitor, the electric field is normal to the plane of the loop. So what do you think is the answer? So there is an electric field that is constant between the plates of a large capacitor, and there is a closed loop which is moving normal to it. So what will happen? First of all, it is moving in which region? It is moving in electric field which is constant. Correct? See, actually, I can't explain this concept now because you need to know something called as Maxwell theory. There is something called as displacement current that you need to know, which will come only in 8th chapter. I don't know why they asked the question here. Okay. Only then you will understand it. But as of now, you can write the answer as no because the electric field is constant with respect to time. So you can induce current by changing the electric flux. But here what is happening? The electric flux is constant.
Constant.
Because Electric field is constant, area is constant, theta is constant. Right? Shall we move on to the next one? Third, there is a rectangular loop and a circular loop moving out of a uniform magnetic field region to a field-free region with a constant velocity v. In which loop do you expect the induced EMF to be constant during the passage out of the field? So first of all, tell me, will there be a magnetic, will there be an EMF induced in both the cases?
Yes, sir.
Because when the coils are moving out, there is a change in
Flux.
the change in flux is due to which parameter? Magnetic field, area, or orientation?
Sir, area.
Very good. That is what I was expecting. So there is a change in magnetic flux because there is a change in area. Okay, so there is no doubt in that. But if you look at the question, they didn't ask us about what did they ask? In which loop do you expect the induced EMF to be constant during the passage out of the field region? Means the induced EMF should be constant with respect to time. So what is the formula for EMF? EMF is equal to d phi by dt in terms of magnitude. Or I can write delta phi by delta t with respect to magnitude. So the EMF will be constant if the change in flux is constant for a given amount of time. Means at every second, there is a constant change of flux taking place. Yes. You can say that the EMF is going to be constant. Correct? So here the flux itself is changing due to whom? It is because of the area, right? So when the circular coil is moving out, is the area that is moving out going to be a constant?
No, sir.
Because in some part, this much area would have come out. In the next part, this much area would have come out. Third part,
Yes, sir.
third second, this much area would have come out. Whereas in the case of a rectangle, what will happen?
It will be
If
same.
this is the amount, so the amount of area that is coming out will be constant. So in the case of a rectangle, we can say that the EMF induced is constant. Does it make sense?
Yes, sir.
Okay. Next one. Predict the polarity of the capacitor in the situation described in figure 6.9. So here, if you observe, it looks like a two-dimensional diagram, no? So how to find which side you're seeing this? See, whichever you're able to see these dotted lines.
Yes, sir.
So whichever side the dotted lines are getting extended till the center of the circle, I repeat, whichever side the dotted lines are getting extended till the center of the circle, that is the side you are actually seeing.
Sir, then in both sides, there are lines that are extending to the center of the circle, sir.
No, 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 no. This is getting cut here, no?
Sir, which is getting cut, sir? I can't understand.
See, this dotted line, right? This is the center, no? I'm putting a blue
Yes,
color dot. That is the center of the circle.
Yes. Yes, sir.
So let me call this as first dotted line and second. Whether first dotted line is coming towards the center or second dotted line is coming towards, which one are you able to see? Exactly meeting
Sir,
at the center.
second one, sir.
That is what I told.
Okay.
Means the first dot, actually, see, that is also coming towards the center, but you're not able to see because the coil is placed in such a way.
Okay,
You're able
sir.
to understand?
Yes, sir.
So whichever you are able to see the dotted lines, you assume that your eye is on that side. Then if the north pole is moving this side, from this side when you see, there will be a north pole that is getting generated. When the south pole is moving close to this, what would have happened? There will be a south pole getting generated here.
South pole.
So south pole means current will flow in clockwise direction.
Clockwise.
So when current is flowing in clockwise direction, which side should be positive and which side should be negative?
Sorry, A will be positive, B will be negative.
No, da. How? Actually, they made a mistake.
Sir, no, sir. A will be negative and B will be positive, sir, because
But the answer
A is
the answer
attracting
they've given-
electrons
Yes, but
and
they've given
B
the
is
answer wrong.
producing the electrons.
Yes. Can someone please check in your textbook if there is a correction done in the latest version?
1 minute, sir. Sir, can you tell me the page number, sir?
212.
Okay, sir. No, sir, that's the same mistake, sir. You have to change it.
Then only thing we have to check is how is the loop's orientation. But you understood the logic, right? So when the
Yes,
north
sir.
pole is coming, this side is going to be north pole. When the south pole is coming, this side will be south pole. I have to check on how they have actually taken the diagram to be. Okay, based on that we can decide. But I'll check this alone then. So as of now, we'll understand the logic that this is north pole and this is south pole. Let me think about this clearly and I'll get back tomorrow. Okay. So one last point to be noted for today's classes. Lenz's law is based on the concept of conservation of energy. Please write it down. Lenz's law is based on the concept of conservation of energy. Okay. So the remaining things you guys can just go through the textbook. The next class, I'll be starting an important topic that is called as the motional electromotive force, and we'll be doing a problem based on it. There's an important problem. Okay. There's actually a small chapter only. We'll be able to complete in 3 more classes. Next Monday, it will be done. Okay. Or Tuesday maximum. So that's it, guys. So that's it for today's class. Revise this concept and come for tomorrow's class. We will discuss the remaining topics. Okay. Any other doubts from today's class?
No, sir.
Okay, then we can wind up.
Thank you.
Thank you, sir.
Yes, sir.